Billahi minash shaitanir rajim. Bismillahirrahmanirrahim. Dear students of class 12th, our topic today is magnetic, a Bohr magnet placed in a uniform magnetic field and hence the torque on it. So torque on a Bohr magnet when it is placed in a magnetic field. Let us consider a uniform magnetic field B from left to right, and let a Bohr magnet of magnetic dipole M is placed such that it makes an angle theta with the direction of the magnetic field. Let the length of the Bohr magnet be 2L. So the force experienced by the North Pole and South Pole is equal to MB, where M is the magnetic strength or pole strength of each pole. The direction of this force at North Pole is along the direction of the field, and at the South Pole, the direction of the is opposite to the direction of B. Now these two forces, they form a couple because they are two equal and opposite forces acting at 2 points, and hence they will try to rotate the magnet in the direction of the field. Now the torque between these two is equal to either force into force R, that is force Fn, and now the action of force, distance between two forces is given by, we draw perpendicular from S and N. So Sn is equal to L, and the force are equal Np, and Np is equal to 2L sine theta. 2L sine theta. So force is equal to Mb, small m, b, and 2L sine theta. So m, small m, and 2L, that is give us the magnetic dipole. So that's Mb sine theta. So we can write it in vector notation m cross b. We can write it as m cross b, and this is analog to the electric dipole in a uniform electric field, where the torque on the electric dipole in a uniform electric field of E is equal to P cross E, where P is the dipole, electric dipole moment, and in case of Bohr magnet in a magnetic field, it is m cross b, tau is equal to m cross b. Now work done and potential energy of Bohr magnet when it is placed in a magnetic field. Work done on rotating a Bohr magnet. Let at an instant magnetic field, magnetic dipole, that is Bohr magnet B, make an angle theta with the magnetic field. So torque is given, just we have found it, it is m cross b, that is mb sine theta. In order to rotate this against this torque, in order to rotate the Bohr magnet against this torque through a small angle d phi, work done by the action force, work done, that is dw is equal to tau into d theta. So dw is equal to mb sine theta d theta. So work done in moving from the initial orientation phi 1 to phi 2 can be found in integration of mb sine d theta. So it is mb minus cos phi, so that is minus cos theta 1 minus theta 2, so mb cos theta 1 minus cos theta 2. If the initially it was at pi, if it is at pi, we can see that, and then theta 2 is 0, then we will have mb cos pi by 2 minus cos theta. So it will be minus mb cos theta, or u is equal to minus m dot b. So potential energy of a dipole or a Bohr magnet placed in a magnetic field is given by m dot b. And you can remember that when we have studied about the electric dipole. The electric dipole is placed in a uniform electric field. Then the potential of that electric dipole is equal to E, that is P dot E. That is electric dipole moment dot product with the electric field. So this way we can now are able to find the torque acting on it and the potential energy a Bohr magnet possesses when it is placed in a uniform magnetic field. Thank you.